Welcome everyone. I'm happy to talk a little bit also about HPC integration and what we do at IQM in this regard. Unlocking complex problems with quantum HPC integration. The way we approach this is actually in a very product-oriented way. So our approach is actually to bring products out there into the HPC centers and then work together with the customers on this HPC integration and basically take the learning on both sides, as we have to, I think, educate quantum people on HPC and HPC people also on quantum. So this is really the approach we are taking. And you see here, actually, we're doing this globally meanwhile. And you see, I think, some of the also more prominent names in the HPC sector, like Jülich, LSAT, but also Oak Ridge here in the US has one of our systems. On the product side, the kind of workhorse that we're really using for the HPC integration is the, we call it the Radiance quantum computer. In the end, you can see it always like the latest generation of quantum computer that you can get from us, and it's also it comes kind of as an upgrade model, so that as an HPC center, usually if you look into the future, you want to make sure that you also have the kind of highest performing computers in a few years, and this is really what we're trying to achieve here, to make sure that the HPC centers and our roadmaps are aligned, and we do this together. We do have a few other products in the portfolio. One smaller brother, we call it Spark. It's really for education, and this is targeting more the university landscape, so that we can actually get quantum engineers out there, and I think we all know how hard it is to kind of recruit and the big shortage on talent. So this is not so much about HPC integration. You see it's much more open, much more modular. You can come with your oscilloscope and plug it in there. If you wish, you can even exchange electronics and whatnot with this device, and also on the software side. And then also we have a cloud offering. This goes more into the kind of use case development in the end. But as said, for the HPC integration, we really use the big devices. And if you look under the hood, actually you see there's already there lots of complexity. And then, of course, we need to make sure that this complexity gets properly integrated into the HPC side. So typically for the superconducting computers that we use, there are different parts. There are the cooling pieces, so like compressors and gas handling systems and the like, to create the low temperatures. You see this on the far right of the picture. Then there is a rack full of room temperature electronics. At least today, this is still how we do it. Maybe in the future, we bring the electronics also into the cryogenics. So there's the typical 19-inch rack, and then in the middle, there's this kind of cryostat, and you see then these golden chandeliers usually. And what we try to achieve already here, you see this, is kind of, it falls into this 19-inch footprint. So we try to design the whole product, though, that it kind of also from a footprint point of view integrates nicely into these kind of 19-inch setups that you have then in the big computing centers. And then basically what we do is we ship such a device to the HPC center, and we take it into operation, and then we start working together with the HPCs on the integration, especially on the software side, of course, as well. And in the end, what it comes down to, of course, is performance. And just in the previous panel, people were discussing like when do quantum computers outperform big supercomputers? And here we really, as a community, still have to boost also the quality of the chips and the size of the chips. And here are just a few examples. The numbers like Crystal 20, 54, and so on, they indicate how many qubits are on the chip. And the main message here is actually not in the details, but if you look at the fidelities, the main point is that the fidelities, they don't degrade when we increase the chip size. And I think this is a very good message, because if you achieve this and you do a proper system design, then you can actually start scaling, and then you can put the error correction layers and other things on top. And I think this is the main point here, that we achieve very good qualities. We are below this error correction threshold to actually start implementing it. And then if we increase the chip size, the quality doesn't go down. And this is what we want to achieve in the end. And also to show you a little bit kind of how the field evolves over time. This is not just one example. If you go deep into the chip and look how the qubits are arranged there, usually the way you implement the logical operations is that you have these coupling elements in between, and this is how you implement the gates. And we have been working very hard over a longer period of time. You see there that the years since 2022 or so on improving, for example, just this coupling element and making sure that when it's off, it's really off. Often you have some residual kind of interaction, so the idle state is not really idle. And then if you apply a gate, that it's really high quality. And you see kind of how the quality improves over time. And of course, we still have targets to go better, but it shows that it's kind of very systematic engineering over the years that goes into those systems. And the way we do this actually in IQM is we approach this in a very holistic point of view. So we, in the end, we offer a full stack system, but we focus a lot on the processor itself. And for this, actually, we have really optimized our innovation cycle. We benefit a lot from the fact that we run our own chip fabrication facility. So we tape out our own silicon wafers with the quantum chips on it. And we have actually also developed our own design software. And this kind of allows us to really accelerate these kind of cycles and do a tape out every few weeks or so. And this is actually much faster than you would see in semiconductor industry or other places as well. And that's actually something also that we do together with HPCs, because these simulations of the chip are not that trivial, as many of you, I guess, know. And we're working, for example, quite heavily with CSC here in Finland and their ELMA project on the chip design. And I like this example because it's kind of, it shows that on the one hand side, HPCs can benefit from quantum computing, but also we actually benefit a lot from the computing power there in the development of our product. And I think this is how it's supposed to be, that we really work hand in hand together and as a community really proceed going forward. And if you do then these things right, and this is something, there's lots of technical numbers, but actually something that we are quite proud of is that meanwhile for all basic operations on the chip, we exceed fidelities of more than 99.9%. And this is really kind of world leading amongst other peers, of course, but this is really where you want to be, and this is then where in the future the error correction then kicks in, because if you achieve these numbers, you're really able then to start putting error correction layers on top of it. And you need to achieve these fidelities for all operations, not only 2-qubit gates, also readout, reset, and single qubit gates, obviously, as well. And then on the error correction side, actually, something that we have been working on a lot, and this is something that now also we do in a much stronger fashion together with HPCs, is trying to figure out how does the software layer look there, the decoding part, for example. Probably you need quite some compute power on the decoding side, but also how efficient can you actually implement this? And we have been working a lot on novel error correction schemes, and one way we do this is actually by increasing the connectivity on the chip. So on a superconducting chip, usually qubits only have nearest neighbor interaction, so one qubit can maybe interact with 4 neighbors or so, however you design it. And we have been putting a lot of effort actually in very novel designs where you saw this on one of the previous slides. Actually, we have a system where one of the qubits can interact with 24 other qubits. And this high level of connectivity actually allows you to decrease then the overhead on the error correction side. So you need less physical qubits to build one logical qubit. And if you compare this, for example, to surface code, which is one of the gold standards, I would say, in the industry, with these more advanced codes, we can reduce the requirement by a factor of 10 to 20, depending how you run the simulations. And this is something that we're really excited about going forward. Also work on this then together with the HPC centers. Okay, a few examples I just wanted to give you at the end on what are we doing concretely. One example from Finland, where we connect one of our quantum computers with the LUMI supercomputer. This was the first kind of attempt to do this, and here actually the connection is remote. So the LUMI computer is in the northern part of Finland. Our quantum computer is in the Helsinki area in the southern part. And this is just a remote connection, and they play this kind of ping-pong game for variational algorithms or stuff like this. But at least what we did here is kind of the software integration, and nowadays you can do things like Slurm schedulers and others. So this was the first things we did. And then the second step was actually that we brought a quantum computer physically into an HPC center, and the first time we did this was in Munich at LRZ. And this is really now, you see the quantum computer there on the same floor right next to the other devices. And I think the first big learning is that the machine still works in the same way as before. So we are not seeing any degradation because of like floor vibrations, electromagnetic vibrations, temperature or whatnot. And you really, in the end, you need some kilowatts of power for electricity and some cooling water. And then if you have this, which most of the HPCs, I guess, have, we bring you a system and it just works. And this was for us, of course, a very good learning there. And once you have this, then you can, of course, start working on the software integration. And our approach here is that we try to be very agnostic. And we heard already in the previous panel, there are many ways to do this in NVIDIA CUDA or a circuit, or a circ or a Qiskit. And we try to have adapters to all of them. But we also build kind of very streamlined solutions then with individual HPC centers to make sure that our system actually works together with whatever they have already developed on the software side. So this is one of the services that we offer actually to work together with the HPCs and really bring it together, because this is not our core expertise. We know how to build the quantum part, but we are not the ones who have kind of the core expertise on the HPC side, and we want to be open and collaborative here. And then we want to use it, of course. And in our view, there are two ways of using it in an HPC environment. The first one is this iterative way. So this kind of ping pong that I mentioned. You do something on a quantum computer, you do something on the HPC, and then you iterate this. And the other way to do it is basically sequential. So you prepare something on an HPC, then you have only a certain task in the quantum computer, and then you go back to the HPC and you just run through this once. And if you look at a few examples, I think one of the more prominent ones for this iterative one is the variational algorithms, for example, the VQA, right? And you have basically, you prepare an initial state, and then you solve something on the quantum computer, you kind of define a cost function, and then you have just an optimizer out there running this. And I think this is now one very standard way of doing it. What we have been working on a lot is actually trying to do more advanced things and really make use of the HPC as well. And this is just one example where actually we have integrated now our quantum computer in a much bigger workflow of HPC. And I don't go into the details of all the boxes, but the main message is there's lots of stuff then going on in all of these boxes on the classical side, and actually only one box, the trial wave function, works on the quantum computer. And this really shows that you can find examples where we need the HPC, but then you probably get some benefit also somewhere, and this is where the quantum computer kind of accelerates and helps. And this is something that we are quite excited about, because it really, I think, in the end uses the power of both. Another example that we did in the Munich system together with UCL is a kind of chemical ground state simulation for molecules, which is also different to the way that many people do it, again, with this variational quantum eigensolver approach. So this is not using this, but this is actually mapping the system, so the molecule that you want to simulate, into the qubits. And then the quantum computer just acts as a sampling machine. And the solution is then calculated on the big computer. And at least our belief is that this scales better in the end than the VQE. Many people are still doubtful of the scaling of the VQE if you go to larger and larger systems. And we are quite excited actually about this. And also, we did a lot of work then here on the software side, and this is the code to run it, and you see it's just 50 lines of code, so it really makes use of everything that had already been developed on the HPC, and it just plugs in the quantum part there somewhere in the middle. And then if you run it, the nice thing is that you get also nice results out. And here, so again, this is about the molecular simulations. And there are, of course, other methods to do this, like Hartree-Fock or the density matrix approach. And now the way we did it in this kind of quantum HPC approach, we reached this chemical accuracy. Of course, this is still for a small molecule, just a few atoms, and you can still, of course, do things like this also on normal computers, but our view is that now, as we start scaling up the systems, we should then at some point also be able to really outperform a kind of a purely classical approach with this one. All right, so I hope I gave you a little bit of insight of what we do in IQM on the technology side, how our computers work, and especially then how we try to integrate them into HPC centers in this very collaborative approach, just bringing our systems on-site, on-premise, and then work together with our customers on solutions. So thank you for your attention.